So we did the following test. This shows you just a photograph of the test apparatus. You see here our test plates mounted in the controlled temperature holder. This is in that test chamber where they're exposed to freezing precipitation, essentially artificial freezing mist. There's another photograph of a larger set of plates. We made the following modifications to better simulate highway de-icing. Instead of looking at bare aluminum, we coated the aluminum plates with asphalt cement to better simulate an asphalt road surface. We left aggregate out of the coating on purpose. We did some initial tests where we tried to use an actual real-life aggregate asphalt, but we had a lot of variability problems, and it cracked, and there was a number of test issues. So we settled on just using asphalt cement with the assumption that chemically the surface is going to be pretty much like an asphalt road surface is going to be. We used a test temperature of 15 degrees Fahrenheit as sort of a mid-range temperature over which we would do de-icing. We did not incline the plates. Unlike the aircraft test, we kept our plates completely flat. And this was also done intentionally. Of course, real-life highways and roads are going to have inclinations varying all over the place. Some are going to be steep, some are going to be relatively flat. We wanted to avoid differences between different de-icer liquids that were due to viscosity or thickness. Some de-icer blends will be thicker than others, and this will make them tend to flow off of an inclined surface more slowly than others, and it will affect how long it lasts. So that's not, that's a legitimate thing to look at, but it's not the aspect we wanted to focus on in our test. What we wanted to focus on was chemical differences. So we kept all of our plates completely flat. We applied liquid at an application rate equivalent to 633 gallons per lane mile. And before you pause and you feel the brakes come on and say, whoa, that is, again, a very unrealistic application rate. Again, my explanation here is that we're not trying to simulate an actual anti-icing event in the field. We're trying to understand how one drop of liquid behaves when it's exposed to freezing precipitation on a roadway. And if I use a real life application rate, I'm going to have one drop here and one drop there. And what we found is that it makes it very difficult to see what's going on. So on purpose, we use a large application rate of liquid to basically make that entire test plate act like one drop. We want to see how that fluid responds to the ongoing freezing precipitation. So we apply our de-icing liquid and we expose our plates to freezing precipitation. We watch what happens. This is what we see. If there is no de-icer on the surface, what we see is there is an immediate and a rapid accumulation of this very characteristic white snow-like rime ice. Now compare that to what we see if there is a de-icing fluid on the plate. In this case, we're looking at a plate that's been treated with plain salt brine. Now after 20 minutes of freezing precipitation, note that there's no white rime ice present. Of course, that's just what we would expect. Because the de-icer is there, it's melting the precipitation. So at first, all that happens is we start getting an accumulation of ice melt on the plate. Then as time goes by and it continues to be exposed to more freezing precipitation, that melt layer gets diluted and it builds up, and at some point it begins to freeze at about 40 minutes here. It starts forming this translucent glaze ice layer. Now, is that the failure point for my de-icer? I don't know that it is. There's a couple of interesting things to note here. The first is that this initial glaze ice layer is completely non-adherent. It's not bound to the asphalt surface at all. You could push it off with your finger. Secondly, it's very fragile. It's very weak. You could break it up just with gentle pressure from your finger. And I don't think that at this stage of freezing, this is going to be the kind of maximally hazardous situation that we're most worried about. So let's see what happens if we go to longer times. As we continue to expose these coupons or these plates to freezing precipitation, for a while that transparent glaze icer continues to grow. And then after about 80 minutes, we note a transition. Suddenly we start seeing what? That same white rime ice that we saw when there was no de-icer present on the plate. And at that point, that white rime ice just takes over and it starts to build and and accumulate. So this raises an interesting question. Since the white rime ice is what shows up when there's no deicer present, and it takes a while for it to start showing up when we've got a deicer present, is the white rime ice an indicator of when that surface acts like it's no longer got deicer on it? That is it an indicator of the relative lifetime of the deicer? Well, we were curious to see if there were additives that would affect how long it took for this white rime ice transition to occur.